This is grade 12 University Physics, Unit 5 Modern Physics, Lesson 2 Mass Energy Equivalence. Now let's look at a couple examples. The first one is we have two balls moving towards each other with the exact same speed. And once they collide, they move away from each other with the same speed. So what can we say about the masses of the two balls? Well, if we look at momentum conservation, we realize there's a ratio between the masses and the velocities. And in this case, since the speeds are both the same, the masses must both be the same. But what if we looked at the situation where one ball was moving slower than the other ball? They collide and they move apart, still moving their respective speeds that they were going before the collision. Well, if we look back at this ratio from momentum conservation, we see that the slower ball must have greater mass. This is very important. We're going to get back to this. But let's look at this example where we have both balls also moving horizontally and vertically. Now their vertical component has the exact same speed. So when they bounce off of each other, the vertical component, again, their speeds hasn't changed. So what can we say about their masses? Well, similar to our first example, their mass must be the same. But what if we were to move alongside the second ball, horizontally? From our point of view, the second ball wouldn't have any horizontal speed. It would only have a vertical speed. But the other ball would have a much larger horizontal speed. Now let's say the speed is very, very close to the speed of light. And so we have to take into account relativistic effects. And from our point of view, the time that we measure it takes for the second ball to go towards where they collide is different from the time it takes for the first ball. From our point of view, it seems like it's taking longer for that first ball to actually reach that middle point. And if the time is longer, its speed is also slower. Now this goes back to our second example where if the speed is slower going in and out, its mass must be larger. But all we did was start to run beside the second ball. So if we look at this ratio for momentum conservation, and we look at the times, and we look at relativistic times, we'll see that the mass is larger by the Lorentz factor. And so, special relativity and time dilation lead to an increased mass, or effective inertia. Now let's look at a slightly different example. Here we have a brick with no momentum, just sitting there, and we have two photons which are coming from either side. Now the brick is going to absorb these photons and gain energy E. And therefore each photon has an energy a half E. Now the momentum of the brick is 0, but the momentum of the photons is not 0. If we look at the equation from quantum mechanics where momentum is Planck's constant over the wavelength, we multiplied numerator and denominator by frequency, which is just multiplying by 1. We'll notice the top numerator is energy and the denominator is speed. For speed of light, c. So the momentum for each photon would be E over 2c, because each photon has an energy of E over 2 in this case. Now if we were an astronaut just floating by, from our point of view, it looks like the brick is moving vertically upwards. And therefore the photons are also moving at some angle. Now if we were to look at the momentum of these photons, we would see that the y component is E over 2c times the sine of the angle. Now if we look at that sine of the angle, it equals the velocity, the upwards velocity, divided by the speed of the light. And the speed of light is the same in any frame of reference, so we're going to put that as c. Now the x components will still cancel, but the y component of momentum doesn't cancel, it adds. But this is a little strange because we haven't changed anything, we've only changed our point of view. But if we were to look at the final momentum and have it equal to the initial momentum of the brick plus this change that it's experienced, which would be the momentum of both photons hitting the brick, we rearrange our equation a little bit. We know that the velocity must cancel in every case, and therefore it's the mass that must have changed. And if we rearrange, we see that the change in energy equals the change in mass times the speed of light squared. Now going back to our original case, if this brick is moving very, very fast, then its mass increases due to time dilation. And so we say its energy equals the Lorentz factor times mass, because we had a change in mass there, times the speed of light squared. Now let's manipulate this equation a little bit. If I multiply this equation by 1 plus v squared over c squared minus v squared over c squared, and I can do that because I'm just multiplying the right side by 1, we can rearrange and simplify a little bit. And what you'll see is that we get E squared equals mc squared all squared plus, now right here we have the relativistic momentum P squared times c squared, which is the full equation. Now if we want to go back to our E equals mc squared, this only works for a particle that is at rest and therefore has no momentum. So if we cancel out P, we take the square root of both sides, we get back E equals mc squared.